I would like to thank the organizers. It's a pleasure to be here in between friends and mentors. So you have to decide whether you're a friend or a mentor. So what I'm going to talk about is a series of recent numerical work that we did in the context of the glass transition. So testing in computer simulations, random first order transition theory. So it's a large number of collaborators, mainly belonging to this Simon's collaboration that is generously funding us. Okay, so I have almost the same first slide as Giulio. So I'm starting from the mean field picture of the glass transition, and I'm using again this Franz-Parisi potential that has been introduced by the people in the room. So the figure is almost the same, that you've seen it several times, and I'm going to use it as a guide for different temperature scales that we are going to discuss in the computer simulations later. So this is this Franz-Parisi free energy. So at high temperature, you have the simple liquid, and you have at least 3 important temperature scales in that problem. The first temperature scale that I'm going to discuss a little bit is when the convexity of this free energy starts to change a little bit, and let me call it the onset temperature. So a second temperature that Giulio has discussed a lot is this mode coupling transition, where you have this flat mode appearing and this secondary minimum of the glass that is emerging close to this mode coupling transition. Then in between the mode coupling transition and the Kaufman transition, you have this secondary minimum in the Franz-Parisi potential, meaning that the glass phase is metastable with respect to the fluid, and the free energy difference between the glass and the liquid is precisely the configurational entropy that Jean-Philippe has discussed a lot. And then as you approach to the Kaufman transition, you have this entropy crisis. So the configurational entropy goes to 0, and the glass becomes the true equilibrium phase. So within mean field, you have at least 3 sharp transitions, which is this onset, which gives rise to this random field Ising model critical point that Giulio already discussed. We have the mode coupling transition, and we have the Kaufman transition. So we'll be discussing these 3 scales in the rest of the talk. So of course, RFOT theory is not about only the mean field limit, but it's also about doing predictions for finite dimensions and thinking about finite D fluctuations. So the key issue, of course, of all this story of going from the mean field limit to finite dimensions is to define and think and take into account metastability in finite dimensions, which is hard to define. So how do you define the states that you count in the configurational entropy? Then how do you define even the configurational entropy in finite dimensions? And how do you think about activated dynamics totally absent from the mean field picture, as we heard several times already? So there are at least 2 sets of things that you've heard before. So in terms of important length scales, a purely static reasoning that Jean-Philippe and Giulio have discussed in terms of this point-to-set correlation lengths, it's introducing a way to think about metastability in finite dimensions by saying that metastable states exist up to a finite length scale, which is this point-to-set length, which is directly related to the almost the inverse of the configurational entropy with this exponent theta that I'm going to discuss a bit later. The second bit, it's about the dynamics that Giulio said is the most important thing in terms of understanding supercooled liquids approaching the glass transition. So here we know very little, but the assumption is that the dynamics below the mode coupling transition, it's activated over some kind of correlated domains given by this point-to-set correlation length, and that is this psi dynamic exponent that Jean-Philippe has introduced already. So as we heard in Giulio's talk, analytic treatments of finite D fluctuations for the statics and even more for the dynamics are very complicated. So the path that I'm going to take now will be to use simulations to address these very big questions that we would like to answer. So the big question is, okay, fine, you have this very complete, elegant theory coming from finite dimensions and thinking about large dimensions and thinking about finite D, but does any of this survive or even exist in the physical dimensions 2 or 3? How do we define configurational entropy? Can we show that there is an entropy crisis? Does the decrease of the entropy even control or drive the dynamics and then the glass formation? Can we see these length scales that you are talking about? Is it possible to measure the critical exponent that people have been introducing in that field? And other features that you would see in 2 or 3 or 4 4 dimensions that are totally not present in the mean field descriptions. And this is what we would like to do as people doing computer simulations. I will not answer all these questions, just to phrase how we think about the problem and why computer simulations may be interesting in that context to test the theory. Okay, so when we do computer simulations, we do simple but not too simple models. So the trade-off is something like very simple particles, hard spheres, soft spheres, Lagrange spheres, something like this. We take polydispersed systems to prevent crystallization, but apart from that, this is what we do. So you use your favorite tool to do simulations, Monte Carlo, Brownian, MD, whatever. Whatever the method, if you do ordinary computer simulations, the best you can do nowadays is to cover about 5 interesting decades of the glassy dynamics. The first 5 decades you can simulate, and then your computer becomes too slow. And so it means that in terms of the temperature scales that I mentioned before, you're almost stuck near the mode coupling crossover. So in between this crossover and the experimental class transition, you have something like 8 orders of magnitude in terms of the relaxation time to reach TG, the experimental class transition. But we know that the experimental class transition itself, it's far from the Kauzmann transition that we would like to observe. So it seems totally hopeless. Okay, so the method that I'm going to use in the remaining of the talk to do this simulation is this swap Monte Carlo simulations that, to my knowledge, was introduced by Giorgio and Greger in the context of glassy dynamics. So the method is very simple. So it's a Monte Carlo simulation. So you do 2 types of moves. So from time to time, you take a particle, you try to make a translation, and then you accept or reject with the normal Monte Carlo rules. And the swap move is the following. You take 2 particles, and you try to exchange the identity of these particles from time to time with a finite probability. And that's all there is into the algorithm. So it's very simple. The only parameter that you can tune actually is this probability to do translational versus swap moves. So you have to optimize for this, but that's it. So the scaling with n is perfect because there is almost no additional computing time to do the swap moves. Equilibrium is automatically ensured, so it has to work. The question is, how good does it work? And very early on, there were very negative answers to this question. So there are 2 papers that are key, I think, in this story. So just a few years after the Greger-Parisi paper. So Dave Reichman in New York tried the algorithm, and he crystallized immediately everything he simulated. So he said, it's a good algorithm, but it's hopeless to study the glass formation because you cannot use it. In particular, you cannot go even below TC where the ordinary simulations are stuck. The second paper is this paper, which is trying to quantify how much of a speedup you get with the swap, and the algorithm, the answer was something like 2 orders of magnitude independently of temperature. So 2 orders of magnitude, it's good, but it's not good enough to maybe motivate you to implement the algorithm, especially if it's crystallizing more easily the system. So that was the situation, and the short story is that if you work a little bit harder on the size distribution and the parameters of the model, you can do much, much better than the 2 orders of magnitude. You can do a lot of orders of magnitude. So the trick to do this is to tailor the size distribution of the particle to have at the same time a broad enough size distribution that you don't crystallize those models, and you have sufficiently many families in your particle that the swap moves are well accepted. So you tailor the system for the swap moves, and you tailor it against the crystallization as well. And this is one typical result that we had. So that was the PhD thesis of Andrea Ninarello sitting somewhere in the room. And this is, in a sense, the striking feature. So if you do ordinary Monte Carlo simulation, this is what you have. This is the relaxation time. These are your 5 interesting decades of glassy dynamics. And here you stop because the simulations take 2 weeks or 2 months. Okay? Now you put the swap on, and you see that the relaxation time, the time it takes for the algorithm to reach equilibrium, it's sped up by something like 4 orders of magnitude, almost at the mode coupling transition here. But the miracle is that the swap can continue to thermalize the system at much lower temperature, larger pressures for this hard sphere system, And at this blue box, if we try to estimate the relaxation time, it's close to the time scale of a typical experiment, so 10 to the 13 orders of magnitude of dynamic slowing down that we get by extrapolating this thing. And the swap here, it takes something like 2 orders of magnitude to relax. So it means that at TG, the speedup is something like 11 orders of magnitude, and the algorithm survives even below TG. So it means that the algorithm is actually extremely, extremely efficient to thermalize system in the experimental, up to the experimental regime and even below. So consequences for today, it means that we have a new tool to really access low temperatures that are relevant for experiments, and also in the regime where RFOT theory is making prediction. So we can now go there and really test directly the theory if we want to. Okay, so the good thing of computer simulation is you can measure almost anything you like, even these complicated cavity things or overlaps or free energies you can access in the computer simulations that you wouldn't have in an experiment. And I remind you that the swap is going anyway below the experimental class transition these days, at least for some of the models. So what I'm going to do from now on is a few recent works that are trying to test this key assumption of RFOT theory and make numbers for the key quantities that the theory is introducing. Okay, so the first thing that I would like to discuss is one of these 3 temperature scales, which is this mode coupling transition. So it's the less clean thing in this business. So what about this mode coupling transition? So we started from a sharp transition in mean field. And what we understand, even within the theory, is that at best, in finite dimension, this is becoming a sharp crossover or a not so sharp crossover. So we don't know. There are tons of papers that have been published to try to decide whether the crossover was sharp, not sharp, or totally absent. And it's a highly debated question that I don't want to settle today. And one thing that you cannot really do easily is to really access the dynamics below the mode coupling transition. So it's hard to see a crossover when you only see one part of the window. So the swap Monte Carlo, it allows us to do static computation, thermodynamic measurements below the mode coupling transition, but the static quantities, mainly, they're almost insensitive to crossing the mode coupling crossover. So for instance, the Franz-Parisi potential in finite dimension would show nothing across the TMCT. So what do we do? So we just recently revisited an old thing that has been developed mainly in Rome by these people, and that was, again, inspired by the mean field theory of the glass transition, this idea that across the TMCT, you make a transition from a non-activated to an activated dynamic. So you have this geometric transition that's exactly realized in the context of mean field spin glasses, for instance, where if you look at the potential energy surface, then above TMCT, you would be close to saddles, and below TMCT, you would be close to minima. So that has been discussed and investigated a lot about 15 years ago. And it has been checked in several computer simulations at the time. And so we take this dashed line here from this early simulation, and this is the number of unstable modes that you have as a function of the temperature rescaled by the mode coupling transition. And the conclusion at the time is that if you look at the stability of the stationary points of your energy landscape, then the stability was going to 0 at the mode coupling transition, suggesting something like a geometric transition happening at the TMCT. So what you do, you take an equilibrium. So you take an equilibrium configuration and you reach the nearest stationary points in the steady state, and you look at the stability of this. So you have to do this algorithmic thing of going into the energy landscape. And then you look at the closest stationary point and you look at its stability. Okay?
But I guess I don't understand why that should be relevant. It's a mathematical construction, but why is it relevant?
Again, this geometric transition is exactly realized in the context of, say, p-spin model. This is what Jorge has shown before. If you have this, if you look at the stability of the finite temperature state, then you have that across the mode coupling transition in these mean field models, you have saddles that disappear at the mode coupling transition.
You understand the finite dimensional thing, not the mean field model.
Yes, but
why is something relevant?
I'm telling you, I'm trying to test this in finite dimensions, taking inspiration from mean field. What's wrong with that? So that's the question. So at the time, it has been tested over, say, between 5 and 10 models, and this is how this fraction of unstable direction in the landscape was going to 0. So of course, now that we have this new algorithm, we can comfortably go below the mode coupling transition and check for this quantity, and we find that actually this power law breaks down completely, and this fraction of unstable mode doesn't show anything close to the mode coupling transition. But the story is a little bit more interesting, and this is where non-mean field effects are coming in. So if we look into the details of how these saddle modes look like in real space, we find two families of saddle modes. And we find that the most unstable modes, they are completely localized. That is, they involve a finite number of particles. And if you look at the modes that are less unstable, they are delocalized. They involve an extensive number of particles. So that defines something like a mobility edge here. And if we measure this mobility edge for many different systems that we've looked at, this edge goes to 0 at the mode coupling transition. So it means that if you decompose these unstable modes into localized and delocalized modes, the quantity that actually goes to 0 close to the mode coupling transition is the fraction of delocalized unstable modes. And this is the result of that study. So it means it's true in the mean field limit, we have these perfectly well-defined geometric transitions. If we go to finite D, it's completely hidden by the emergence of these very localized unstable modes. And I should say that this idea that in finite dimensions you have these localized modes that appear, it's emerging everywhere in computer simulations of glasses these days. If you look at vibrational modes, if you look at shear rheology, you have these very strong non-mean field localized things that are emerging everywhere. And that's typical of a non-mean field effect that you capture in the simulations and are completely absent in the mean field limit. So as maybe Daniel is suggesting, I don't know, the link with the dynamics and what we observe at finite temperature, it's still missing from this description, and it's not been done yet.
Can I talk about an analogy? So in the Ising model, there are lots of percolation problems that you can define in the Ising model, where you have percolation of spin in different ways and so on. But they don't have anything to do with the physics of the Ising model. And I guess I don't understand why these things, except for mathematical construction, have to do with what the finite dimensional physics is.
I'm not sure I'm the one to try to convince you. I just told you that I'm not sure how connected to the dynamics that is, and I'm told you that this transition is totally hidden in finite dimensions. So I shouldn't be the person trying to convince you it's an important thing. Okay. So maybe the best answer, if you go back to this, here you have the development of this flat mode close to the mode coupling transition that has been studied at length in the context of these mean field systems.
We know that long-term free energies don't exist in finite dimensions.
I know, that's all what my talk is about. So thank you for emphasizing that. Okay, so precisely this. Okay, so this is a measurement of the Franz-Parisi potential in finite dimensions. And what I want to show is three messages from this. So this is now the Franz-Parisi potential measured in a three-dimensional hard sphere system. So if you want to measure this free energy, you have to learn how to measure free energy from standard textbooks. And the idea to measure that quantity is to really look at the overlap fluctuations and to try and measure in the simulation extremely rare overlap fluctuations. Then you take this P of Q, you take the log, you divide by n, and you get the free energy. So this is reasonably easy to do. It's demanding numerically, but it's doable. So this is what the Franz-Parisi potential looks like for a typical 3D hard sphere system as I crank up the density towards the glass transition. So as Daniel Fisher was pointing out, this secondary minimum that you have in mean field, it cannot exist because in finite dimensions, the free energy has to be convex. Nevertheless, you see three things. The first thing is that the fluctuations of the overlap or the Franz-Parisi potential, they become non-trivial even in three-dimensional system. You don't have these typical Gaussian fluctuations, and you have this tail at large Q that develops. So that's directly the sign that the phase at large Q, the glass phase, is becoming metastable with respect to the liquid. So So out of this, we can do many things. I'll do two things today. First of all, I will extract using this mean field recipe a configurational entropy that is going to decrease as I approach the Kaufman transition in this system. And the second thing I would like to discuss, and I will discuss in the next slide, is this idea that Giulio introduced, that if I introduce a field conjugate to develop here, I'm going to tilt the potential, and I will induce a first-order transition. So that's what I'm going to do in a minute, and the configurational entropy I will discuss in a few slides. Okay, so constraint phase transitions, I'm repeating this here. I add a field conjugate to the overlap, and I'm tilting the potential, and I'm trying to induce a first-order transition that would be here for this system. So what I do here in this plot, so this is the work of Benjamin Ghislain here in the audience. So I'm looking at the dependence of the overlap as a function of this field. This is an isotherm, so this is a high temperature system where the overlap increases rather smoothly. Then it grows through a critical point here, and below that temperature, then I have a first order discontinuity. So I have a discontinuity that vanishes and closes at this second order critical point here. So Benjamin has worked hard on the simulations, and now we can go to relatively large systems and observe this phase transition. So we go to super large systems, I would say. So in terms of observing the first order transition, I think we are confident that we are seeing one. And Benjamin has worked hard enough that we can now try and test using finite size scaling the universality class of this second order critical point here. And for now, the results that we have are fairly consistent with the random field Ising model universality class for this endpoint. Okay, so all this then is a direct consequence of the metastability of the glass phase here, and then it's in a sense a signature that there is a non-trivial point to set length scale developing into this system. So in terms of the mode coupling transition, we had this debate about how relevant that was, so that was a debate. In terms of the onset temperature, this critical point, there is no doubt, I think, from the computer simulation that this is surviving perfectly well in 3 dimensions, and the properties of this are exactly the ones that Giulio had discussed before. So that was the onset, that was the mode coupling. So now let's try to go towards the Kaufman transition a little bit. Okay. So what about configurational entropy and trying to reach this ideal glass transition? So many things should be said about the configurational entropy. I told you that the best thing to do would be to measure the Franz-Parisi potential, look at the free energy difference, and measure this as a function of your control parameter. So we did that already. Another thing to do would be to do essentially what experimentalists or what previous simulations have done, that is subtract from the total entropy some kind of vibrational entropy, and then the remaining thing would be the configurational entropy. So all these methods have been available in the last 20 years. They are well defined, they're cheap, but we know that they cannot be a correct definition of the configurational entropy, but they are simple alternatives to the Franz-Parisi potential. So this is what we did. It required a little bit of technical things that were fun to do, but now we have this method that works super nice, super easily. It's very cheap, and we can, for instance, for the hard sphere system, easily measure the configurational entropy up to super large densities in equilibrium simulations. So that's the second thing.
So there you mean entropy is actually entropy per particle?
Yes. Yes. Yes, it's intensive, yes. Okay, the final thing that I wanted to discuss about around this idea of configurational entropy is this point to set correlation length that has been again introduced in the previous talk. So that's the idea of using frozen boundary conditions to force the glass phase into your cavity and then see when the liquid is going to win as you increase the size of your cavity. So the critical nucleation length in the sense for the fluid is again related to the configurational entropy. It's a difficult computational problem. We know how to measure these things for small and large cavities, high and low temperatures. And there are 2 useful outcomes, I think. So the first outcome is that if you measure this as a function of the temperature, you can discuss and prove that you have a growing static length scale accompanying the glass formation. And this is essentially what this first series of studies had been doing. They were looking at whether we could detect the emergence of an interesting growing static length scale as we approach the glass transition. So we did that as well, but one thing that we can do is we can invert this and take the measurement of the point to set length as, in a sense, a measurement of the configurational entropy. And this is, in a sense, another route to define a configurational entropy in finite dimensions where, in a sense, metastable states cannot be defined. So this is the route that we have taken to get access to another estimate of the configurational entropy. So if we collect everything I said before, so this point to set length, this historical version of the configurational entropy, and this constraint phase transition of these Franz-Parisi estimates of the configurational entropy, we do this for a hard sphere system in 3 dimensions, and this is what we get. So we increase the pressure as we go from the right to the left, which is like decreasing the temperature in thermal systems. So this is entropy versus temperature plot. So most previous simulations had measured the configurational entropy in this regime above the mode coupling transition. So now we can access this blue square, which was the exponential glass transition, and we can go a little bit below for that system. And in a sense, what we find is not too surprising. It's what experimentalists have been telling us for the last 70 years. That is, we have this steep decrease of the entropy, and if you try to do any kind of reasonable extrapolation, it's going to be happening at a finite temperature. Not that we don't use the approximations that experimentalists are using. So in a sense, we use quantities that are very close to what the theory tells us to measure. And on top of it, we have a direct real space interpretation of this decrease of the configurational entropy. And despite all these changes, in a sense, the insight of the last 70 years from experiment, it's surviving of having a finite Kauzmann transition if we extrapolate the data in 3 dimensions. Okay, so this plot has been shown already in 2 dimensions. So we've implemented the swap algorithm in various dimensions. So 2 and 4 and 5 are in the work. So I'm showing you the result for 2 dimensions because it's published already. So the idea is to see, okay, let's go to 2 and 4 dimensions to go away and closer to the mean field transition. So in 2 dimensions, the discovery is that the swap is working super, super efficiently. So someone asked about the relaxation time for that system this morning. So this is the physical relaxation time, and this is where swap is taking us in equilibrium conditions. So if we put numbers, here the last points that we get is something like the exponential glass transition divided by 3. And this is, again, all my estimates of the configurational entropy. And again, if we simply use polynomial to extrapolate where this entropy is going to vanish, we find something that's super close to 0. So we say, well, the Kauzmann transition for that system, it's really close to being at 0 temperature. And as I think you heard Giulio say, this is a useful guide for what, say, the lower critical dimension of the Kauzmann transition could be. And in a sense, for me, finding that there are systems where you can extrapolate the Kauzmann transition to 0, it's giving me confidence that when I extrapolate to finite temperature, then maybe it has some physical meaning. Okay, so 2 more things before I think I finish. I haven't checked the time. So what about these static exponents? So remind you that the static exponent was the connection between the point to set length and the configurational entropy. I just told you that we know how to measure these things. So we just eliminate the temperature and we do a parametric plot of the configurational entropy versus the point to set length. And then we fit the data we have with some power laws, and we get values for this exponent in 3 dimensions and in 2 dimensions for hard spheres. So there are 2 predictions in the air for this interface exponent, so d-1 and d divided by 2, depending on which paper you read. And the data in 3 dimensions cannot really decide between the 2. The data in 2 dimensions are much cleaner, but in 2 dimensions, the 2 predictions are equal. So, okay, so we just confirm them. So what I would say about this theta exponent is that we have all the tools to do much better measurements now. Not only 5 points for one system, but we could do much better, including data in 4 dimensions where these 2 exponents would be very, very different, and maybe we could try and decide things about this theta exponent in the future. Okay. Final exponent that has been discussed is this dynamic exponent psi. So that was this activated scaling where the relaxation time is related to the exponential of the point to set length to the psi. If you combine everything together, one way to try and decide from both simulations and experiment the value of this exponent would be to make a plot of tau versus the configurational entropy. That plot would then have a free exponent, which would be a combination of the psi and the theta exponent that we just discussed. So again, we have two types of predictions for this psi value, d or d divided by 2. And we've looked a lot at tons of real experimental work where the entropy and tau were measured, and we did that also in the computer simulations. So what, again? Yeah, I'm not yet there, but yes, yeah. So we looked at different liquids, and we have done the same for the computer simulations. And when we plot tau versus 1 over Ts, which would be the canonical Adam-Gibbs relation with this alpha exponent being equal to 1, and if we look carefully in the right time regime where we are below the mode coupling transition and approaching the glass transition, we find that systematically we have deviations from this linear relation, which would be the Adam-Gibbs relation. So we find that if we look at the right time window, the Adam-Gibbs is not satisfied. This exponent is a bit smaller than 1. And if we estimate the exponent psi from this, we have something where the psi is close to 1, even in the regime approaching the experimental glass transition. So this is where we are at the moment. I'm not too optimistic that we can do much better to estimate psi, because getting the dynamics below the glass transition will be really, really difficult. So this is where we stand on the psi thing. If I may take 2 minutes from my, okay. So I wanted to close with this idea of self-induced disorder. So I borrowed this from Julio's slide that he sent me kindly yesterday. So he talked about this idea that when you look at the free energies and the Franz-Parisi potential, it's important to think of the large system as being made as a mosaic of small systems having local fluctuations of the disorder. So can we do something from computer simulation? It's just the question I would like to raise before finishing. So the local fluctuations of the Franz-Parisi potential, they may destroy the Kaufman transition, that was Giulio, and they may be useful input into an effective field theory for the glass transition. So the only thing I've been thinking of doing, and this is work with Gilles and Benjamin, is try to measure the Franz-Parisi potential in super small systems now, in systems of the size of the point2 set length, which is fairly small, and try to go super low in temperature to see what kind of fluctuations we get in the Franz-Parisi potential. So if we do this, we can get an estimate from the value of this critical epsilon field to induce a first-order transition, which would be this free energy difference here, which is local fluctuations of the configurational entropy, and in the language of effective field theory, that would be local fluctuations of the random field in the theory. So these are just results that I have. So this is overlap versus this field epsilon. And these are sample-to-sample fluctuations of this overlap versus epsilon field for fairly small systems. And for the last pressure here, I'm much below the experimental glass transition. So in a sense, the critical field to induce this first-order transition is fluctuating quite a bit in those small systems. Quite a bit means by a factor of 2. So it means that if you try to estimate the configurational entropy in these small systems from position to position in space, the entropy is changing quite a bit. Okay? A factor of 2, it's enormous, because when you put that into the time scale, then it's creating broad distribution of relaxation time. So this is what we've been able to accomplish now. Now it's time to quantify all this. And the final thing I wanted to show is this question that has been asked so many times. So, okay, you have a decreasing entropy, you have an increasing relaxation time, you maybe have some kind of correlation between times and entropy. That doesn't imply a causal link between dynamics and entropy, and that was the case, I think, via argument of the other day. So one thing that we can do with this small system is the following. So for one small system, we can measure the local entropy. And for one such small system, what you can do is measure the relaxation time of the system. So what I'm trying to propose here is try to measure the local entropy and the local relaxation time and try to see whether this Adam-Gibbs-like relationship holds at the level of the fluctuations in real space. So this is just the results. It's a scatter plot of measured relaxation time versus measured configurational entropy in this fairly small system. I was surprised to find such a good correlation between the two. So this is the preliminary conclusion. Okay, so that's my conclusion. I'm a bit over time. So what I'm trying to say is that we have now this swap algorithm that allows us to test directly in the computer simulations the core hypothesis of the theory. So in a sense, we can either challenge or fit the theory with the computer simulations. I've told you that we have ideas on many of the quantities, but I think many of the quantities we have not quantitative answers yet. So this exponent theta should be measured. Many more systems should be studied, and we should look at this self-induced disorder in more details. And so that's why I'm giving you rendezvous for next year. Thank you.
Thank you, Ludovic. Do we have any questions? Nick.
I'd like to ask a naive mathematical physics question.
Okay.
So we know that if you have, so I want to talk about equilibrium in a rigorous sense, and so an equilibrium in Gibbs states. Okay? And if I'm talking about a spin model with discrete spins, then I know how to prove that basically the entropy of or the decomposition of the Gibbs state into pure states cannot be extensive. It must be sub-extensive. Okay. Now I don't know how to prove this in the case of some continuum, a part of the continuum. So my question is does it actually make sense to have decomposition, which I think for you, in your terms, might be the decomposition of the configuration space into its ergodic components? Does it make sense for this to be extensive? Is this possible in a finite dimensional system? Or am I too naive? Are we supposed to assume that this is not really what's happening?
So I'm not sure exactly what you're asking. So the entropy of the liquid, of course, it's well defined. So the quantity that mean field theory is dealing with is what I call the configurational entropy. So I said there are many things to be said about it.
Configuration entropy is the entropy of this decomposition. It's counting how many
exactly.
components there are.
So that was one of the first. When I said big questions in finite dimensions, the first question is how do we define states? And if we cannot define them, your question.
How to do this.
Yeah, we don't know how to do it. I agree with you. So as soon as you leave the realm of mean field theory, it means that this complexity that vanishes in the context of mean field theory, that quantity is no longer defined. So when you go to finite dimensions and you say, I'm going to measure a configurational entropy, trying to quantify how many free energy minima I have, then it's an ill-defined question, and I think this is what you're trying to say. I think everybody in the room would agree with that.
Well, I think it's a well-defined question. It's to the answers that are...
Yeah, exactly.
There is one thing that can happen, which is that the free energy function, fluctuation function, can have a linear function. This can happen. It cannot be non-convex, but it can have a part which is and you can define the difference. The ending point of
Well, to do with the question how you would define Q in a large system as well, which in 2 dimensions is going to get completely swamped out by phonon-like modes.
No. So we don't. We know how to deal with those things. So that's not an issue even in 2 dimensions. So the question is not how to define the overlap or dealing with the phonons. I think the question is really the question he is asking. You do the Silvio proposal. You say I'm going to measure the free energy difference between the large Q and the low Q thing. This is well defined, and then you decide to call this the configurational entropy.
To Gibbs states, the free energy density,
Yeah.
okay, which I think is what you mean,
Yeah.
is the same for all, any Gibbs state. At least I know this is true in spin models.
Yes, what I'm trying to say is that this free energy difference is no longer related to the number of things.
That's the question whether Q is well defined. I mean, it's still...
Q is well defined, yes. What?
If I may say,
Yes, let Peter have a say.
mathematical physics to actual physics. When you look at the plot of SC, the experimental plot of SC, say extrapolate through to the
Yes. I don't have it.
for many of the substances, if you look at the absolute entropy measured by the fact that things are described by quantum mechanics in the crystal at 0 temperature, it goes negative, not very much lower than T0 for most of these examples. So there clearly is a problem whether or not the solution is replica symmetry breaking or not. There clearly is a problem with continuing that extrapolation.
So therefore you can't get into extrapolation, okay? I mean, Couchman, this is the 30th anniversary of a conversation I had with Couchman, who said, I don't understand why anyone takes my paradox seriously. Obviously it doesn't extrapolate to 0. And I guess I haven't heard any arguments to make.
Well, I would say that for practical people, the extrapolation is not really, the only question is, can you predict properties about actual materials under actual circumstances? And the extrapolation is decent in that regime. I don't think Couchman would disagree with that.
Well, this is a fascinating discussion, but perhaps we'll just have one more question.
This fact that the psi exponent is approximate 1, is that related to expectations being string-like, or does it have another?
I mean, it's a good question. I don't know. The only honest answer I have is that to get to this one value, you have to make a string of small decisions, even dealing with the experimental data. So we cannot make psi larger than 1, even by adding a small prefactor. Whether it's strictly 1 and whether it's related to something physical, I don't know, because to know you would have to look into the dynamic close to TG, and even in the, if I give you an equilibrium configuration near TG, I don't see how it's going to relax because I cannot do simulation. So testing your idea that the excitations there are linear, I cannot do it directly. So I'm just like you, I'm trying to guess whether it's true or not. But it seems like a very small value indeed.
Okay, I think we must bring the session to an end this morning. So let's thank all the speakers again.